I'll tell you the history of this talk. I was very excited about the problem of narrative and episodes and events when I received this invitation, but I didn't know that most of you were basically visual artists rather than narrative artists. Is that right? Some of you are narrative. All right. Well, I'll get to the narrative at the end then, and I will talk about that. But I thought I'd review the history of what seems to have been the thing that caught everybody's fancy, which is the holographic paradigm, and tell you by going through the history and ending up with this book and ending up with narrative, essentially where things stand. Now, let me go back to 1950. This is very hard on me because I haven't a clue as to what you folks are thinking. Usually I talk to an audience. I'm talking to some light spots where your glasses are reflecting what's going on. So please, let me say this. Just stop me if you can't hear me. Can you hear me in the back? Yes. Okay. If you can't hear me or don't understand something, just wave your hands or do something to let me know. That's a little better. Thank you. Let's go back to 1950 where Karl Lashley wrote a paper. I was present at the time he wrote it. It's called In Search of the Engram. An engram is a memory trace, and it's a specific memory trace. For instance, a memory trace of that little poem you just heard. That would be an engram of that particular trace, of that particular episode, if I can use that word. So he wrote this wonderful paper, the upshot of which was that he, Karl Lashley, had spent his lifetime searching for the engram in the brain and for engrams in general, and that the only conclusion he could reach is that learning was just not possible. And he added to that, that seems to be the case in the classroom, but other times we do remember a few things, so he wasn't giving up hope. Well, that was one statement. Another one was by Gary Boring, who wrote a history of psychology, and he was saying that the time was not ripe for psychologists to pay any attention to the brain because, after all, we knew nothing about how the brain worked if we couldn't even begin to tackle the problem of memory. I mean, we had no way of knowing how the brain organizes memory. Now, the word memory is used in two ways, in two very different ways, by biologists and psychologists. When a biologist talks about memory, he's talking about storage. Something is stored. When a psychologist talks about memory, he's talking about remembering. Whatever had been stored must be retrieved in some way. And so right there, right at the beginning, if you read anything in this field, you have to know who's saying what, because it's two very different, two different issues are at stake. Well, there's another set of problems that we didn't know much about, and that was perception. Interestingly enough, this book that that has just been published is on perception. When I went to Stanford from Yale, I had just done some experiments in which I had put aluminum hydroxide cream on the brain, which caused epilepsy in monkeys, not epilepsy of the kind that people have. This was done in the visual system, and there were electrical storms that were produced, and these animals could still do all of the discrimination performances, all the tasks, visual tasks that we gave them extremely well despite these electrical storms. And so Wolfgang Köhler at one point made the statement, now you've disproved not only my theory of perception, but everybody else's. With that, I went to Stanford, having taught sensory physiology at Yale, and said, the one thing I'm not going to teach is perception. Well, as usual, fates have it that the very thing you want to escape catches up with you. One day, it was about 1963, 62, 63, Jack Hilgard, who had gotten me to come to Stanford, was rewriting his textbook of psychology, and he says, what's happening in perception? I told him nothing is happening, certainly not as far as I'm concerned. We're not going to, I have nothing to say. And he says, well, I'm writing a textbook. Those of you, there are few here I've met who are physicians, and you know the situation. You don't know what to do, nobody tells you what to do, what it's all about, but you've got a patient sitting in front of you. Well, it's the same with writing a textbook. What are you going to say? What are you going to do? I mean, you can't just waffle and say, I don't know anything, you know, that doesn't work. So he said, I want you to tell me what is the best idea. Well, I said, Wolfgang Köhler's theory was about DC potentials, sort of electrical fields in the brain, but big fields that had the same shape as that which you perceive. If I look at your face, there's an electrical potential of something sort of roundish with two things like that and a slit down here, you know, some kind of field potential like that. Well, I'd disproven that. The other idea was one that is still in all of the textbooks. It was started in the late 1950s with the finding by Hubel and Wiesel that, in fact, that certain cells in the visual cortex respond best when an illuminated line is projected, the line at a certain orientation. Now, if you look before you get to the cortex, essentially the cells respond best to spots of light. But as you get to the cortex, lines. Now, you've all been to grammar school. You all know Euclidean geometry, and spots make lines. From lines you can make surfaces. From surfaces you can make three-dimensional objects, volumes, and so on. Well, this was essentially what Hubel and Wiesel suggested, and in fact it is true that when you have convergence of the cells below the cortex onto the cortical cells, you do in fact get some convergence like that that could account for these elongated receptive fields, as they're called. These cells that respond best to elongated stimuli, lines, edges. Now, there's Hubel and Wiesel got the Nobel Prize for this finding sometime later, in the early 70s. And it certainly is a persuasive way of looking at it, but there are some problems to it. Problems which made me, at least, very uncomfortable, and many people in psychology very uncomfortable. If I have to make up your face from a number of lines, think of how complex that is. And some people have the hair on their heads, others have hair on their chins, and each of those hairs have to be separately encoded into a total picture, a grandfather cell, as it was called. Furthermore, as I approach closer to one of you, that image changes. I mean, right now, your head subsumes a very small angle, visual angle in my retina. But if I get close, wow, you know, it gets very big. I mean, so there has to be a cell for every inch of the way that I come, or centimeter if I'm going to be scientific on this, you know, about. So the whole idea that we could build up our perceptions from such elements seemed very awkward, despite the fact that occasional grandfather cell was found. In one case by one of my grandchildren, as it were, a student of mine. Well, so I began to look into this myself and do some research in the laboratory, and found that in fact these cells that are selective of single of lines at different orientations were also selective of a lot of other things. Color, luminance, how bright an object is, how quickly an object goes by, the direction of motion, the velocity of motion, acceleration of motion, different things. And each of these cells was different in its propensities of what it responded to. I was telling Carol this afternoon, I had Dave Hubel on a symposium that I organized for the neurosciences at one time. And I said in introducing him that, that I had found this, and he knew the same thing. And he said, yes, I was right. But it had occurred to me in trying to classify cells that my experience with women was that if you said, I love you because you have such beautiful hair, or if I love you because you're so bright, you get slapped in the face, or she gets angry for some unknown reason. And you always end up saying, I want you to love me for me. I'm not just hair. I'm not just a brain. I'm me. I'm all of the things. And women don't want to be classified. And it took me many years to learn that. Then I said, it took me almost as many years to learn that about cells in the brain. They don't want to be classified. Each is individual. Each has many propensities. There are blondes and there are brunettes. And some have blue eyes and some have brown eyes. And some, some like this slant and some like that slant. Each cell has a whole set of propensities that makes it rather individual from any other cell. Well, Dave Hubel got up and it was a wonderful symposium, a true symposium. Symposium, you're supposed to drink beer. Well, we didn't have beer, but we had wine, jugs of wine so everything was nice and loose. And he said, I've never learned that about women. I haven't learned it about the cortex either. And it was really great. So anyway, so this began to be, this is why that particular way of looking at it was didn't seem sympathetic to some of us. There was a third alternative, which Karl Lashley, my mentor and very dear friend, had proposed, called interference theory, which simply said there are waves in the brain, and as these waves propagate, of course, they form rings, waves, if you drop a pebble in a pond. And so the waves form, if you drop two pebbles, they form rings, and the rings interfere with each other. They have places where they cross, and there they either reinforce each other or cancel each other out. And he suggested that, and we had talked about it many times, and I said, where do these waves come from? And he hadn't a clue. And I also asked, well, even if we did have waves, how could it cause a perception? How could it deal with either memory or perception? This seemed to be absolutely impossible. And he finally wrote a paper saying, I had a bright idea, but I can't figure out how it might work. Well, this is early 1960s we're talking about now. And there was Hilgard. What should I tell him? Well, I told him everything I've told you, and I said, I have a pretty good idea that Köhler was wrong, and there are certain things wrong with the Hubel and Wiesel type of thing, which is in the textbooks. I think we should pursue Lashley's idea, because at least we don't know he's wrong. We don't have a clue as to what he's talking about, but at least he's not wrong. He hasn't been proven wrong. So I went to work with my lab group, and I simply told them one noon at a meeting, I said, look, I haven't a clue as to what Lashley was talking about. Is there anything we can come up with that would at least give us an idea of how this works? Lo and behold, within a week, I mean, if you think about synchronicity and somebody looking out for you and all of this sort of thing, within a week, we found an article. One of my colleagues, Nico Spinelli, found an article in Scientific American, And he said, you know, these waves could be just ordinary things that happen in the brain. John Eccles, who later also received the Nobel Prize, John Eccles pointed out in an article called the, what did he call it? Neurophysiology of Imagination. Had a lot of neurophysiology, a lot of imagination. He's a dualist. He didn't tie the two together very much, but that doesn't bother him very much either. Later he did. He and Popper wrote a beautiful book tying these things together. But at that point it didn't bother him, but he said, look, when I study, and he really was a wonderful man who could study, put very fine electrodes in the brain and find out what is going on between neurons, where they join together. Said, when I study these things, I'm studying one at a time. But that's not the way the brain works. He said, every nerve fiber breaks into all of these branches, and every time anything happens in the nerve, any nerve impulses go down, all of these branches are activated, and what you could conceive of all of these potential changes, these electrical changes at the ends of the fibers in terms of waveforms. Well, this is what's good about listening to people who are brighter than you are. It was the answer to the first half of the problem. Where do the waves come from? They are there. They are very straightforward synaptic potentials, postsynaptic potentials actually, and Eccles had, you didn't have to do anything, you just had to look at the data that were available in a new light, and he'd done that for me. I'll tell you another story, however. He and I were giving a talk together, two talks, in St. Louis, and he was talking about free will. And he was talking about Kornhuber having discovered waveforms in the brain prior to one's action. He said, well, that shows the brain decides and makes decisions as to what you're going to do before you actually do it. Free will. And in that he said, well, Kornhuber had this wonderful discovery, but he really doesn't know the significance of it. So then I got up and told this story about finding Eccles' neurophysiology of the imagination, and I said, well, unfortunately, Dr. Eccles really doesn't know the significance of what he found. Exactly what he'd been saying about Kornhuber, of course. And he got a kick out of that, and so did everybody else. It was a lot of fun. So there was the first half. Another week later, my issue of Scientific American came out, and it had in it holography by Leith. Yes, my issue of Scientific American came out a week later, less than a week later, and it had an article in it on holography by Leith. And a hologram is this kind of an animal, which I'm sure you've all seen, but I thought I'd bring one along because it, yeah. Okay, let's see if I can. Now, if you'll turn out the lights, I think I can show you that there's something here. It isn't very good. I have no laser beams with me. I borrowed this from Carol. But do you see what I see here? Do you see anything? They nearly didn't sell me this in San Francisco. It was.
I don't think we can see it from over here. There, okay.
You'd like to get a little better look at these ladies, but considering, do you see? Now, the reason for showing you this, have you all seen, anybody here not see it? Did you all see something? Could you identify what it was?
No. Not from this angle, but it's okay.
Could you see that it was two figures, some? Yeah, okay. It was two girls, one kissing the other or something, doing something interesting. The reason I brought this along, if I can, is to pass it to you so that you can look on here and see what the brain physiologist saw in the brain. Nothing. Nothing. Exactly. When you look, go ahead and pass it around, and people, you see, all that's recorded there is the wavefronts that are produced by an image. When you make a photographic image, you take the intensity of every point of light and record it on the film. And you do this by getting the light to come through a lens to the image plane, which forms the image then. Now, if you don't have the lens, then all you record is these wavefronts. Because if the light in this room, there's another demonstration which I can't do, but which is very interesting. If I just take a projector and show you a slide, and then take the lens out of the projector, leaving the slide, I can show you that by putting my glasses in front of the part of the screen that's illuminated, you can get an image anywhere. So the light in this room is all over the place. It's refracted. And again, none of the textbooks show this. It's not well known in visual science, and not documented certainly, that the light here is splashing off me and off of that board, as you know from trying to take television records of this, and so on. It's spread all over the place. And if you didn't have lenses in your eyes, you wouldn't see objects the way we see them. Now, the interesting thing about this is everyone in audition and hearing, in the hearing sciences, knows this. Because in hearing, we have the problem of creating concert halls. And you know, if the reflections aren't just right, the concert hall is either too alive or too dead, or it may be just right until you fill it with people and their clothes and their hair absorb the reflections and the concert hall is dead. So we know it for auditory science, we don't know it for visual science. Why? Because people did not conceive of form vision as you have just seen it in terms of holography. That was the big breakthrough. Now, I was writing Languages of the Brain in the 60s, and as it was coming to press, people all over the world were beginning to look at the brain in terms of these wavefronts. I got a letter from someone at Cambridge University, Fergus Campbell, saying, with his first published paper on this, saying, "Is this what you mean, Karl?" And so what happened from about 1965 on through the 1970s is more and more evidence came along that the eye, for form vision, not just for color vision, but for form vision, was acting very much like the ear. That it dealt in terms of frequencies of waveforms. The model that I like to suggest is that that it's very much like a piano. The retina, as is the cochlea, is sort of like a keyboard, and the energies from the outside world operate, they do their thing on the keyboard. The keyboard is connected to the brain in very spatially arranged fashion. That's why laser beams are better for interpreting holograms, because they're parallel. Same thing here. More or less parallel connections between the receptor surface and the brain. There's convergence and divergence, but basically you get a topological correlation. And then each cell in the brain resonates to about an octave of frequency. That's the bandwidth. This is, and the kind of analysis then that is done is not a Euclidean analysis of form, but a harmonic analysis. Well, that started the whole thing going, and the mathematics of this are well known, the mathematics of the lens and how it transforms a scatter, as it were, into an image, and the particular person responsible for that is Baron Fourier. Fourier was a physicist and mathematician around the year 1800, and there hangs another wonderful story. See, I've got frontal lobes, and so I'm making a narrative out of this. He was asked, he and his superior, Monge, were asked by Napoleon to go to Egypt on the Egyptian expedition. And Fourier had been troubled with some problems on heat that he couldn't resolve analytically. He knew mathematical analysis from Euler to Lagrange, and he went to Egypt, and then Napoleon had to go back because of political turmoil in Paris, and he took Monge back with him, left Fourier sitting at the bottom of a pyramid, base of the pyramid, for the next 2 or 3 years. And Fourier never got angry with Napoleon for abandoning him, and my interpretation of this is that Fourier very quickly after he got back wrote a paper on how to do a Fourier analysis. That is, how he solved his problem analytically. And since Arab mathematics was one of the reasons Napoleon went in to Egypt to see if he could find out more about the mathematical sophistication that was present in Islam, not Egypt, but in Islam in general, my interpretation is that Fourier in fact got some ideas talking to these people. That is not, that's maybe true, may not be true. But anyway, when he came back, he did this Fourier analysis, published a paper, it was brilliant, and he got into the French Academy. 2 weeks after he got in, another paper was written by Lagrange, or I think it was Lagrange or Laplace, I've forgotten which one, saying Fourier's proof is no good. And meanwhile, everybody began to use his analysis. This tells you a little bit about science, and especially about mathematics. And people tried the next 50 years, and finally somebody came up with a plausible proof, but it wasn't a solid proof. Fourier analysis kept going. Everybody used it. Fantastic, powerful tool. In 1970, somebody came up with still a better proof, and we have a proof in here going back from quantum physics to the Fourier analysis and Euler and Lagrange, which may be the first definitive proof of the Fourier theorem. I mean, the intuition that that man had that has been good for 2 centuries before a decent proof comes in gives you some idea of what science really is about and not what people think science is about. That's no different from art in what the scientist or the artist does. It's different in what gets accepted, maybe, and what doesn't get accepted, although the marketplace also plays role in acceptance in science as it does in art. But still, we have the same criteria you do as you do in art. We talk about an elegant proof, an elegant paper. Well, what's elegance except beauty? What did Einstein say? This theory is so beautiful it must be right, you know? So that's just an aside. Now, as I say, the data began to come in that indeed the brain was doing something like a Fourier analysis, and the people on the East Coast here were really a little reluctant to get into the fray. They were what we out west used to call feature creatures, whereas we out west were frequency freaks. And the frequency freaks actually spanned over the ocean to Cambridge University and University of Leningrad and other places like that. And so the battle was joined, and we had the idea, the Euclidean versus the harmonic analysis of this. The harmonic analysis turned out to have one further point that was important. And that one had been anticipated in a very strange way again. Some of you heard me, one of you at least heard me back in 1977, and I was telling about how I got in touch with David Bohm. I had gone to my son, who's a physicist, to ask about a problem that we have regarding brain function. One of them is, should we interpret things really in terms of waves, or should we interpret them in statistical terms? And this is the same problem that is present in quantum mechanics, in quantum theory. And, you know, is it a wave or is it a particle? And so I went to my son and I said, I've got to learn a little more about quantum theory because the problems seem to be the same as we have in the brain. I might tell you where that particular issue is going. When you have interference patterns and you have these nodes where things get reinforced or cancel out, those nodes, what Fourier did was he gave coefficients, he gave numbers to those nodes. That's how he could solve the problem. And they're called Fourier coefficients. He simply took any waveform and moved it 90 degrees, that is, where there's a peak now, you move that over to where it's a trough, and he did this for sine waves and cosine waves of the same thing, and there's a, you know, what a sine cosine have to do, they're dealing with triangles and all of that. He worked all that out so that there's an empirical sort of a way of thinking about how to analyze waveforms, but you do it in terms of numbers, and that's why we can do it with computers. So the issue isn't really, is it waves or is it particles? But I didn't know that. And so fortunately I went to see my son, who told me what quantum mechanics is all about, and essentially gave me a very good course in about 10 days, so I appreciated what physicists are up to. Well, I was very grateful to be in psychology and neurophysiology after that, because I figured the physicists didn't know what they were talking about. You know what they say? Here are equations. For heaven's sake, don't ask us what they mean. And we don't want to know, because of this wave-particle duality. There are a few people, however, who are dissatisfied with that view, and one of them, who's still alive, my son said, is David Bohm. Well, I got back to my lab, and my secretary, I told her about this over surgery. I was doing surgery one Saturday morning, and I was telling the story about David Bohm, you know, and how maybe he had some answers to this problem. She said, you know, David Bohm has asked you to come to a conference next fall. I said, he did? And I was delighted, of course, that he had found me and I had found him. And so, in fact, I went even before that conference to listen to some lectures he was giving at Birkbeck College. Now, David Bohm came to the following conclusion, that if you didn't have lenses in our eyes and looked at the universe, either through telescopes, lenses in our eyes, microscopes, the universe would look like a hologram. And he called this an implicate or enfolded order, because as you saw in that hologram that I passed around, you can take any part of it, if you did this right, you can take any part of it and see the whole thing. And in fact, I don't know what this one was made of, but another one that I have that I used to carry around was just cut from a lampshade, and I just took a part of it and took it on my trips. I mean, any part will deal with the whole. Now, so David Bohm and I got to be acquainted and interested, and I listened. Then I went over. London is a little far from San Francisco, but Berkeley isn't. So I went over to talk to Henry Stapp and Jeffrey Chu about every 2 weeks, and we talked about these things and worked on them for about 10-year period. And I went to London and talked to Basil Hiley, and so I knew what the issues in quantum mechanics were. Mind you, what has this got to do with holography? Except that David Bohm said that, the implicate order looks a little. What is a solid evidence that these two things belong together? The connection was already made in the popular press and by Merrill Ferguson and so on, but there was no real connection. Lo and behold, within this was about early 1970s, a group at Harvard, and also in engineering at Harvard, and also one of my computer programmers had to go back to Rome. He was Italian, and he had talked to his brother, who was a mathematician at Canberra in Australia. And everybody was excited about this idea that the brain could indeed have these spread functions, as they're called mathematically, in them. And he went to Peter Bishop's laboratory at his university, the National University at Canberra, and watched the experiments. And they were doing a lot of things on edges. They were not doing anything holographic at all. Doing edges and showing leading edges and trailing edges. Excellent work, really wonderful work. And he said, this is very interesting. The Fourier analysis, if you do a harmonic analysis, goes to infinity. Well, we have infinite brains, yes, but they don't go to infinity, at least unless you splatter them in an accident. There's a limit. And each of these receptive fields, each of these neurons is limited. And then the evidence is that they do indeed respond especially well to edges. So he said, these are not, the brain isn't doing a Fourier analysis, it's doing a Gabor analysis. And so the whole story comes together, believe it or not. Gabor is the inventor of the hologram. He got the Nobel Prize for that, but not just for that. Gabor was a mathematician, and he was interested in the early 40s in the problem of getting a message across the Atlantic cable in the most efficient manner possible. And this message, mind you, at that point, was not telegraphy, where you've got dots and dashes, which are easy to get across, but human voices, waveforms. How do you get a waveform across a wire and pack it as densely as you can so you can get as many conversations across as you possibly can. And it had been pointed out that there was some problem in doing this, and to make a long story short, what he found, what Gabor found and published in 1946 after 3 rejections, of course, of the paper, and so on, and he finally did get it published, but in the proceedings of the IEEE, an engineering journal, you know, comes out each month. They've got a lot of these proceedings. It's well buried. It took me about 3 years to get a hold of one. And it had been referred to in the literature by only 2 people by the time I got going. But interestingly enough, Marcella, who was this young man in Australia, knew about this, and he said these Gabor functions are exactly what is involved. Now, what is a Gabor function? A Gabor function is a Fourier transform that goes to infinity. The waves go to infinity, but it has a limit. It has an envelope over it so that it's truncated. It's just a window on one of these things. And what Gabor said essentially was that there's a limit to the efficiency with which we can communicate across the cable. In other words, we can't compact that any further than a half of a wavelength, because if you get shorter than half of a wavelength, you don't know what the frequency is, and then it all gets distorted. So in order to do that, he did it mathematically and showed it, and he came up using the same mathematics that Heisenberg had used in defining a quantum of matter. In other words, and what Heisenberg had done for microphysics, Gabor did for communication, and he called it a quantum of information. A quantum of information. And that's what the brain does in encoding it. We now had a direct connection between quantum mechanics and how the brain works. 2 possibilities. One is that the brain really does process information in a quantal fashion, that it is doing this at the quantum level. And there are some work that has been done on that, which is in the appendix in the epilogue, quoted in the epilogue of my book. Let me go into that for just a minute. Schrödinger, who's responsible for the Schrödinger equation in quantum mechanics, wrote a book called What is Life? And in it he says, life is superconductivity at normal temperatures. Great statement, you know. This was 1930s he wrote this. Did he go on and say how this is possible or anything? No, just one sentence. You know, superconductivity, normal temperatures. And superconductivity is a quantum mechanical phenomenon. David Bohm has pointed out that many of the implicate order type of things, quantum mechanical types of things, go on in superconductivity. And perhaps we will find in due time that this is true. Other people have shown that membrane physiology and microtubule physiology in the brain and elsewhere could obey quantum physical laws. So that's a possibility. But it was also true of the Atlantic cable. The other possibility is simply that what 20th century all the problems and laws that have been developed for quantum physics are also true in larger situations, in macrophysics, in other words, under certain conditions, and that it is a generalization of quantum physics to macro systems. So those are the 2 possibilities, and in fact, we are looking into both possibilities, hopefully over the next decade or two. Well, so that is what led then to this book. First of all, the hologram, you've seen a picture come out of it, so perception can emerge from something that simply looks like a bunch of polka dots and waveforms and so on and so forth, a hologram. See, the original question, what is going on in here that doesn't look at all either like the physical world or our perceptual world? What's going on in here looks so different, but it can reconstruct. It can remember, in fact, even our memories, because they are also distributed in this fashion. So that if you get a hole in the head, as someone was telling me this afternoon, if you get a hole in the head, size of this guy had, wasn't quite a fist, but almost, and he came away and was no memory loss, no nothing. Everything was working just fine. So that's what this book is about. I have to, you know, it really reviews all of the evidence in various ways, has nice pictures in it, and no math, talks about the math, but no math until it gets to the appendices, which two Japanese colleagues did for me. They are in Japan, and they did this in terms of matrices and all kinds of equations that I can't read, but I had to interpret both the Japanese and the equations and put them into English, and hopefully they're reasonably correct. But that's where things stand. Now, I want to finish up very briefly with saying where this all fits so that we have a reasonable view. I think that there is a paradigm shift, as we call it in science, that perception indeed can be thought of in these holonomic terms, in terms of harmonic analyses, rather than in Euclidean terms where we make stick figures and build up from spots and lines and so on. I think that is coming. It's not completely here, but certainly most of the visual science people already accept this. So that's step number one. That's not all there is to perception, though. Look at me. I'm not just a bunch of waveforms, am I? I'm an object pacing up and down here and doing things, and you're objects to me. All I've been talking about so far are images. I haven't even talked about objects. And let me see if I can demonstrate to you what we think an object is. Why don't you come up here? You might be able to do this most easily. If you just close your eyes and stick your hand out, and I'm not going to hurt you, so have faith. Okay, just tell me what you feel.
Touching my palm.
Thank you. And now move around and tell me what you feel. You can move. Not you, but the hand.
Oh. Okay, I'm holding something that you put in my hand.
Well, what is it?
I don't really know. A knife?
Thank you. Perfect. You may sit down. I chose well. Everybody doesn't do it quite as well, and so I have to be careful. You did. It was a knife, my pocket knife. Perfect. Notice two things. First, you said, you're touching my hand. You're touching my hand. Subjective. Once you started moving, you said immediately it's something. And you weren't moving very much, so I had to move it more, and then you said, oh, it's a knife. But immediately it said, you didn't say, it is me somethinging it, or, you know, it is a something. So it's a set of relations among images. Well, again, mathematics comes to the fore, and we have what's called group theory for this, and it comes directly out of quantum mechanics and even before that, so it's very easy. And here's another moral of the story, and if I can see without my glasses because I don't want to put them on. I will put them on. I just want to read this because it has so much to do with how science is made. Looking back at the development of the holonomic theory of brain function as presented in these McEachran lectures, I am constantly surprised by the following paradox. Giant strides appear to have been made in understanding figural perception during my research career. At the same time, the fundamental approaches that are of a sufficient magnitude to now constitute a paradigm shift were already accepted a century ago by Poincaré, Helmholtz, and Lie. Now, the mathematics that I used is in terms of Lie groups. It's another mathematical, Lie, L-I-E. The story goes that, in fact, the evidence from letters is that Poincaré wrote to Helmholtz and said, you know, if you use group theory, you could talk about how objects are formed. They're relations. Objects are relations. And I've just said relations among images. Why don't you use group theory? You might be able to come up with how objects are formed. So Helmholtz wrote a paper on it, thanking Poincaré. Poincaré gets a letter from Lie. He said, this guy Helmholtz, he doesn't seem to know much math. He's using the wrong kind of group theory. You have to have continuous groups to do what he is. And I've just invented continuous groups just for the purpose of understanding object perception. Now, a century's gone by, and Lie groups have been used by everybody in physics, engineering, and so on. And only once, one philosopher talked about Lie groups as having to do with perception until very modern, until the last 10 years or so, when a fellow by the name of Hoffman brought it back to perception. So we go around, and every 100 years or so we come back to a better understanding of what is going on. All right, we've taken one step, and I've got to take one or two more. You now know that something more is involved in perception than just these holographic things. You've got to put them together, and you've got to use group theory. But you are looking up here, and you see a podium, you see my glasses, you saw the book, you saw me. You've already categorized me as being human, hopefully, and that this is non-human. You've already put names on these things, in fact, but even before names, if you couldn't think of the name, you know you've categorized it somewhere. Well, back in the 1940s, late 1940s, early 50s, we discovered a part of the brain that has to do with categorizing. It's not the part of the brain that has to do with imaging, not the part of the brain that deals with the formation of objects and that movement thing of getting groups together, and it is still further forward in the brain that deals with categorizing. But now things get a little tough, because you've got to have memory in order to do this, and you've got to be a little selective in how you do all this. And this is where attention comes in, and all of the more complicated aspects are what are now called cognitive aspects of perception. And here, again, I've got to read you a very brief thing just to show you how science and art are so closely related to each other. And it's really amazing. Have I not erred in applying to historical thought, which is a study of living creatures, a scientific method of thought which has been devised for thinking about inanimate nature? And have I not also erred further in treating the outcomes of encounters between persons as cases of the operation of cause and effect. The effect of a cause is inevitable, invariable, and predictable. But the initiative that is taken by one or another of the live parties to an encounter is not a cause. It is a challenge. Arnold Toynbee, A Study of History, Oxford University Press. That's what the whole latter third of the book is about. What's an encounter? And here's, in brief, what I was going to talk about. There's a part of the brain that deals with getting familiar with things that occur in the environment. If suddenly the camera back there crashed on the floor, we'd all pay attention, we'd all orient it. We couldn't go on, we'd have that little thing to deal with, we have to get the camera back up and all that. That's an episode. The next orienting response of that sort would be when I get back up here and say, okay, now let's get back and finish the talk, whatever. That's an episode. And I thought that episodes were made up of events, essentially, flowing past us. Well, the mathematics in here and some of the things that the way it went was that didn't seem to work out very well. What seemed to work out was that a novel event, and another part of the brain is involved in innovation, the hippocampus, you heard about the 4 volumes on the hippocampus. The hippocampus deals with innovation, allowing innovation to take place. Now, a novel event comes from the fact that you take something that you are familiar with, let's say steaks, and you go to the store wanting to buy some steaks because the company just dropped in, and steaks have just gone up to $10 a pound. Somebody's on strike. So you get lamb chops instead. Now the event of buying lamb chops instead of steak, that's an event, and is due to the fact that you can equate lamb chops and steaks for that particular episode. It's called, in psychology, has an excellent name called equivalence, equivalence of the same valence, the same value. It has the same value. In fact, the lamb chops are cheaper. So you evaluate the thing. Okay, so now, remember, we've got images, we've got objects. The objects have formed categories, but they're really prototypes of categories, because what you're doing is make them equivalent for a particular episode, and that is then the novel event. You have invented, you've taken inventory, and you've invented buying lamb chops instead of steaks. Usually it's the other way around, but this time it's this way. Innovation. Okay. So that then is the event. So this was a little puzzling to me, but I decided to look up event in the dictionary. What do you think it means? What's an event? Where does it come from? It's the Latin, ex venire. Ex, out, venire, come. Outcome. It's the Latin equivalent of the Saxon outcome. It's an outcome. We make our events. It's a challenge. You see, all this latter part of the book is putting together the evidence that, in fact, the cognitive aspects of perception are not sensory-driven, but that they're memory-driven, and that we create our perceptions to a certain extent. We certainly create our equivalences, that which is the same as under these circumstances, and that then allows us to go on and create true novelty. And then when we string these together which is a function of the front part of the brain. Notice I've started back here, I'm ending up here. With the front part of the brain, I can string these things together into some kind of reasonable story that makes sense. And that is the narrative aspect. And so the narrative deals, in fact, the three parts of the frontal lobe with the propriety of what it is, and that is connected with one part of the limbic system, and the priorities we assign, where does it fit into the story? What comes first? What's going to tell the story best? And finally, the middle part of the lobe deals with making it practical, because you have to get it out. You have to do something and connect it with the middle part of the brain, which lets you in contact with the environment, direct contact with the environment. And so that is the story of the narrative. I've just sort of skimmed over that without giving you all the evidence, but I thought, at least for those of you writers, that you ought to have that aspect. All of this works on the substrate of basically a holographic-like structure, a distributed structure that looks much like that hologram, which is constrained, which has certain limits to it, which make it, each element really, a quantum of information a la Gabor. And that's a story to date. I hope you'll have me back in 10 years. Maybe we can tell you more.